So, speaking of rides, let's look at rides. Cool applications is what I called this. And one of the first cool applications of circles, which has really been the whole theme of our overall unit, we've segued into orbits and gravity, but really that's circular motion as well, are roller coaster loops. So, a roller coaster barely makes it around a vertical loop of radius 4 meters. A says, find the minimum height that the roller coaster needs to start from at the top of the hill. B says, find the normal force or the apparent weight of a 50-kilogram passenger when the roller coaster returns to the bottom of the loop. What does A want me to find? Height, minimum height. Any guesses on what kind of an approach I might want to use here? Energy. Because I think I see a change in height. I think I see a change in speed. I think I see a yucky, curvy path. Let's try that. And we're on the Earth. I don't need to use cosmic energy. I can use MGH. Oh, thank goodness. Well, definitely that's initial. That's initial. I'm going to have final be right there. Okay? Not at the bottom of the loop, but at the top of the loop, because I think I need to take the loop into account in my calculations. And Drake, if I just looked at the bottom, that'd be just like a normal hill. Okay with that? What's the law of conservation of energy? G, Drake? KE, initial, keep going. Yeah, Prince Edward Island is a province, despite my headline that I showed you last day. Equals KE final plus PE final. I think the only thing that's going to cancel, we're going to assume we started at rest, which in real life is actually not a bad approximation. That first hill that you go over on a roller coaster, you're never going all that fast. Okay. Right? 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 Okay. And I know V final at the top can't be 0, because if you came to a stop right there, you'd crash and die. Like, I've seen loops, the coaster's still moving. Oh, I noticed one thing. What? Tori, were you at Disneyland a couple of weeks ago? When you went on the roller coaster, did they make you step on a scale before you got on the roller coaster? No? You know why? Yeah. Was it the happiest place on earth? Yeah. Okay. What are we trying to find? I guess H initial. So I'll divide by G in just a second. But let's walk through here. Oh, you know what? To get rid of that 1/2, I'm going to go times by 2, times by 2, and times by 2. Because Sinead, haha. And that's going to give me 2GH initial equals V final squared plus 2GH final. Here's my problem. I mean, I'm okay with H final, because if the radius is 4 plus 4, 8. I don't know how fast I'm going up there. Wait a minute. What path are we tracing out? Let's try a free body diagram. What are the forces acting on this coaster car at the top? Get the obvious one. What else? Normal force pushing which way? Down. Who's winning? I guess they both are. So it's going to be winner plus winner equals, what path are we tracing out? So look up, don't write this down, just watch. I would think to myself it's going to be MA, but it's going to be MAC because I'm moving in a circle. But don't write this down yet, Drake. Which version of acceleration do I want to use? Ah! Ooh. That'll give me a V, will it? Okay. Kayla, you okay with that little bit of reasoning there? What word did I underline in the question?
Barely.
Barely. What I'm really getting at is you almost feel like you're about to fall. You feel virtually weightless. If you feel virtually weightless, what's your normal force? So because of barely, I'm going to say that. Oh, this is minimum speed, and in real life, you go faster, you want to feel a normal force because you don't want people freaking out. But this is minimum height. You okay with that? That's going to allow us to modify this equation to Tori, were you at Disneyland a couple of weeks ago? You know what is kind of cool? Even if the California Screaming roller coaster has a loop, did you have to step on a scale? Look at that. Now, I was going to get the V by itself, but then I said, wait. Don't I have a V squared here? Why don't I get the V squared by itself? And I'm going to get, I guess, V squared equals grrr. Yeah, we're coming full circle. Get it? Full circle. Okay. Oh, come on. That was pretty. Okay, never mind. So I can plug that into here. Right? All right. So I'm going to get this. 2G initial equals GR plus 2G, and pause. I'm not going to write H final. I'm not going to write H final. Ready? Look at my diagram. What do I call that distance right there? R. So you ready? How far from here to here?
4.
R.
Oh.
Yes? How far from here to here?
2R.
So if I wanted to do a generic height, Robbie, instead of 4, instead of 8, if I wanted to do a generic height, what's the generic height of this roller coaster? Cool, 2R. Whoa, huh? Something weird going on here. What else cancels? What? What's going on? What this means is this roller coaster doesn't depend on Earth's gravity. It will work on any planet from this height. If you somehow had Star Trek technology and you beamed it to the moon, the roller coaster would be safe there. If you ignore all the vacuum and okay, but if you had all were wearing spacesuits, it'll work. Or if you beamed it to Mars, this height won't have to change. It'll still work. That's kind of cool. How would I get the H initial by itself? I could divide the whole thing by 2, but I'm going to go in chunks. I get this. H initial equals 0.5 R, R over 2. And then I guess I have 2 times 2 divided by 2. You know what? Plus 2R. I always love this because we get such a clean answer, and I'm willing to bet any ride designer has this one memorized. You want to know the minimum safe height if you're building a roller coaster with a circular loop? The minimum safe height is 2.5 times the radius of your loop. That is such a nice, clean answer, James. I always smile when I see that, because it could have been ugly. Here, in fact, James, I'll bet you can do this in your head. You ready? H equals 2.5. James, what was the radius of this loop? Read the question. I told you in the question. Go read, 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 read. What's the radius of this loop?
4.
Yep. So I have to be able to do 2.5 times 4 in my head. Go ahead. What's 2.5 times 2? So 2.5 times 4 would be 5 plus 5 in your head? Ta-da. There's the generic expression. Now, in real life, Kayla, you would never build a roller coaster like this. This would terrify people because when they got to the top of that loop, they would feel physiologically like they were about to fall out of their roller coaster cars. They would scream. They would panic. It would not be a fun ride. So what you would really do is you would probably double or triple that height, and that would give you enough of a normal force that you would feel like you were getting pushed into the car safely. You went on California Screaming? Did you, during the loop, ever try bending your head down just before the loop and then straightening your head up? Did you ever try, during the loop, sticking your arms out and just trying to do little... Oh, you missed out. Okay. The reason is also nobody will ever build a circular loop. Now, the one at California Screaming, out of all the roller coasters I've been on, is from a profile view as close to circular as I've seen in a long time. And you feel the G-forces there. If it was completely circular, you'd probably black out and get nosebleeds and whiplash. Really? Yeah. So there's part A. What does part B want us to find? Where? Normal force at the bottom? I guess this is also a job for a free body diagram. What are the forces acting on this roller coaster at the bottom? Get the obvious one. What else? Which way? And I know it's winning because what path is this car tracing out? A circle. So where must the winning force be pointing? Toward the center. So I'm going to have this. Winner minus loser equals mv squared over r. The v at the bottom is not the same as the v at the top, so I can't just move the GR down to here. Right? If you've ever watched a roller coaster, it's going slower at the top of the loop than it is at the bottom, which I guess means, Tori, you have your maximum G's at the bottom. Mm-hmm. Okay. I need that V. Conservation of energy, G. So now, instead of final being at the top, I'm going to redo this, but I'm going to have final be at the bottom. Okay. Kinetic initial plus potential initial equals kinetic final plus potential final. Starting at rest. Potential energy is going to be mgh initial, and I now know h is 10, but I'll stick that in later. Equals a half mv squared plus, oh, wait a minute. What's my final potential energy if I'm on the ground? Oh, nice. Okay, I don't know why that vanished. Let's try that again. So, don't need that. Tori, were you at Disneyland a couple of weeks ago? When you went on the roller coaster, did they make you step on a scale? Really? Imagine that. Cool. You know what? I'm going to get the v squared by itself because there's a v squared in my equation over here, so I'm not going to bother square rooting. I'm going to get, I guess, v at the bottom squared is going to be 2 g h initial. Is that all right? Let's plug that in over here. The normal force at the bottom is going to be mv squared over R minus, nope, plus mg. Did I give the person the mass? 50 kilogram, okay, because here the mass doesn't cancel. A heavier person will feel a bigger normal force than a lighter person. That's why little kids can do amusement park rides so much better than adults. They can handle the G's easier. Okay. M. You know what? Let's do this algebraically and generically first. It's going to be 2 times g. What was our generic expression for the initial height?
2.5 R.
Over r plus mg. Oh, what happens to the r's? That's kind of cool. Looks like I get this. The normal force is going to end up being, well, I have 2 times 2.5. James, in your head, 2 times 2.5. 5 mg plus 1 mg. James, in your head, what's 5 mgs plus 1 mgs? How many mgs? 5 plus 1. How many mgs? Tori, if we actually built roller coasters with circular loops, at the bottom of every loop, you're pulling minimum 6 Gs. People won't like that. Oh, let's actually now crunch the numbers. 6 times 50 times 9.8. $29.40 newtons. For this 50 kilogram passenger, that's what they would feel. But generically, and again, Simone, that's starting from the minimum height, that'll give you 6 Gs. If you build in a safety margin, you're going to be going faster at the bottom, you're going to be way more Gs. So we don't build roller coasters with circular loops. We build them with teardrop-shaped loops. They're called a clothoid loop. If you want the fancy math term, it's a loop of constantly decreasing radius. But California Screaming is as close as I've seen to nearly circular. But if you look at Playland's corkscrew loops, for example, they look much more like this, like a tall, skinny loop, teardrop shaped. You don't feel the G-forces anywhere near as much. Oh, put your pencils down. So, one application, roller coasters. Application number 2 is what we call the conical pendulum. It's a pendulum in that you have a mass on the end of a string, but you may have seen these outside of novelty stores. It's the toy helicopter suspended from the ceiling that's going around in a circle, going around and around and around, tracing out a cone shape, a conical pendulum. So a toy plane is attached to the ceiling with a string, has a little propeller which causes it to move in a circle as seen below in side view. If we ignore air resistance and force from the propeller, so there are 2 forces we're going to ignore. The propeller is pulling it into the page, forwards, but air resistance is pushing out of the page, and they're in equilibrium because it's going around at a constant speed. So we're going to ignore those forces. Which of the following is the best free body diagram for the plane, A, B, or C? Well, let's see if we can figure it out. Here's my plane. What are the forces acting on it? Get the obvious one. Gravity? That doesn't get rid of any wrong answers, unfortunately. What else? Tension. What else? Is there a normal force? Are we on a surface? Okay. What path are we tracing out? So where is my net force pointing? Toward the, but that force doesn't show up on the free body diagram. So I'm kind of skeptical about B because I think they're trying to suck me in. I'm kind of skeptical about A. I think a force pointing outwards, that's that centrifugal force that people think exists, but actually it's just your own inertia wanting to keep going in a straight line at a steady speed. That's why you feel like you're getting pushed outwards, Jocelyn, when you're going around in a circle, but you're not. You're getting accelerated inwards. So I think A is right. How the heck can those two forces give me a net force pointing toward the center? Are they at angles to each other? Well, then why don't I add them together? How might I add them together? Draw them. So I have this. Gravity down. Tension up. The resultant is always from the tail of the first to the tip of the... Julie, do you see? There's my resultant. There is FC. I do have a force pointing toward the center. My net force is towards the center. It's the combination of the two forces. It says explain why the others are wrong. I think a good free body diagram is worth 1,000 words. All I need, James, are those two forces, and that does allow me to have a net force pointing towards the center. It says redraw a force diagram and then write force equations for the toy plane. This motion is referred to as a conical pendulum since the plane traces out a cone in space. Okay, we had gravity down, tension. So Duick, you drew this. You said, change colors, Mr. Duick. Gravity. By the way, how do I know not to stop my tension right there? Because I know what the net force has to be pointing toward the. So I better stop tension right about there. Tension. It also suggests that tension is bigger than gravity, and I think it is. And here is FC. Now, in the picture, they gave me this angle theta, so I notice when tension is next to a vertical line, that's theta. That's theta. Don't draw. You can draw that if you want to, but what I really want you to notice is, see the Z? I think theta is right there. MG, opposite, adjacent, or hypotenuse. Adjacent. FC, opposite, or hypotenuse. Tension, hypotenuse. What trig function relates gravity and FC? So one equation that comes out of here, I guess, is tan theta is opposite over adjacent. What would the sine equation be? Okay. What would the cosine equation be? And really what this means is if you give me the angle, all you need to do is give me one force and I can find everything else. Oh, really, all you need to do is give me the mass, because then I have mg, and I can find everything else. And once I knew FC, I could probably figure out v squared over I. I could probably solve for v if you tell me the radius. I can tell you how fast it's going. Like example 4. Here is a conical pendulum. Says this, the blue ball is swung in a horizontal circle and it completes a single rotation in 1.2 seconds. You know what? I think they gave me the period. I think I'm going to be using the 4 pi squared r over t squared one. Okay. The chord makes an angle of 35 degrees with the vertical during the ball's motion. Oh, they gave me the length of the chord. Okay. What does A want me to find? Okay. Well, centripetal acceleration, I said they gave me the period, yeah? So I think I'm going to start out by going 4 pi squared r over t squared. I think this is going to be kind of plug and chuggish. I think. I know 4, I know pi squared. Do I know t?
Yeah.
What was t? What was it, 1.5? 1.2? Do I know r? Brent, what? You mean we got to get triggy with it? Really? Let's draw a little triangle here. It looks like I have this. 0.44. And then I think if I put a right angle there, Robbie, do you agree? I think that's the radius that we want, right? And that's 35 degrees right there. Okay. R, opposite, adjacent, or hypotenuse. 0.44. Hypotenuse. Okay, which trig function can I use to find r? Sine? Sine of 35 equals opposite over hypotenuse. How would I get the r by itself? Okay, I'm going to be so lazy, I'm just going to go 4 pi squared and then 0.44 sine 35 over, what was t, 1.2 squared? Okay. By the way, this is a nice, the wave swinger, that's the ride at Playland. The circular swings that swing out, those are conical pendulums. Here's the physics of those. Okay? So if you analyze that ride when you go to Playland, what you'll do is you'll time the period, and that's easy to do while you're standing in line. You just time how long it takes somebody to go around once. Then you'll try and measure angle theta, and I'll show you instruments we can use to do that. You're good to go. 4 pi squared times 0.44 times sine 35 divided by 1.2 squared. Do you get 6.91? 6.92? Yeah? Is that right? Duncan, is that right? Oh, am I wrong? Oh, have you guys in math now moved to radians? And so that's one of the habits you're going to have to develop is every physics class, go to degrees, every math class, go to radians. Or some of my students had 2 scientific calculators. They used their graphing one, they kept that one in radians for math, and they had a scientific one from math 11, they kept that one in degrees. But whatever system works for you. Oh, I'm not going to rewrite this, Mr. Duke. I have the answer. What was it? 6.92? It's an acceleration, meters per second squared. Yeah. Yep. B. What's the centripetal velocity of the ball? Well, what can I let that equal? Oh, 6.92, because that's another way to write acceleration. I got to get the same answer both ways. How would I get the r by itself, Connor? So v is going to be 6.92 times r square rooted, which is going to be the square root of, what was r? 0.44 sine 35. And I'll write 6.92, but of course you know I'm going to use my answer button. Square root. Don't forget to square root. And I get 1.32. Okay. What else can we do with these conical pendulums? A 3.5 kilogram object moves in a horizontal circle on the end of a string as shown. If the tension in the string is 42 newtons, A, what's the net force? And B, what's the period? Okay. I think I'm going to start with a free body diagram. I don't know where else to go. What are the forces acting on this pendulum? Get the obvious one. Okay. What else? That's it. I think I want to add those two forces together, but since they're not in a straight line with each other, I think I want to combine them tip to tail. Really what I'm doing is sort of winner minus loser, but I'm combining the forces vectorially. So it's going to look like this. Gravity down, tension up, and that equals FC. Wait. Isn't FC the net force when you're moving in a circle? So when A says, what's the net force? Because it's, how do we find FC? Winner minus loser equals. Okay. That's 18. I think that's 18 because tension next to a vertical line is 18 degrees. They told me tension, so FC, opposite, adjacent, or hypotenuse. Opposite, tension, adjacent, or hypotenuse. You know what? For part A, I think I can go sine of 18 equals FC, which is F net, over tension. I think the net force, centripetal force, FC, is going to be tension times the sine of 18. What was tension? 42? Sine 18. Cool. 12.97, you know what, I guess 13.0. There's my net force. Oh, what does B want me to find? Period. How about I go FC equals M4 pi squared R over the period. Squared. Period squared, right? Now I'm suddenly terrified that I forgot to square it last time. Phew, I did. But the R isn't squared. Good. Phew. Is that right? It's 4 pi squared R over T squared, right? Okay. To get the period by itself, I think I would multiply the T up to the top. M4 pi squared R over FC. That's going to give me T squared. How to get rid of a squared. Yep. Julie, did they give me the mass? How big? Oh, okay. 3.5 and then 4 pi squared. Did they tell me R? Oh yeah, 0.6 divided by FC. I'm going to write 13.0, but of course, Julie, you know I'm going to use my answer button, right? 3.5 times 4 times pi squared. Oh, that's wrong. Pi squared times 0.6 divided by answer button. Square root of that. You get 2.53? So this thing rotates every 2.53 seconds. Put your pencils down.